All right, diving in today, getting into some serious AI with this paper, Command A, an enterprise-ready large language model. That's from Cohere. And, it's not just hype. We're going to break down how they built this thing.
Yeah, you got it. It's all about the engineering here. How do you make a language model that can actually handle what businesses need? If you're learning about AI, machine learning, or you're just curious about what makes these things tick, this is the deep dive for you. We're going to try to pull out all the cool stuff, all the innovations that make Command A work.
So how'd they even start building this enterprise-ready model? What's the foundation?
Okay, so like a lot of these big language models, it all starts with pre-training. Imagine like you give a student this giant stack of books and articles and code, but there's no labels, no explanations, and you're like, okay, figure out the patterns, how language works.
So it's like learning by osmosis almost, just absorbing all this raw information.
Exactly. That's pre-training. The model is basically trying to predict what comes next. In a sentence, a paragraph, a piece of code. And that's how it learns the basic structure of language through this self-supervised learning.
Okay, so what kind of library did Command A get for this pre-training? It had to be massive to be ready for all sorts of business tasks, right?
Oh, it was huge. I mean, they used a multilingual data set. That means it wasn't just English. Think about all the text and code that's publicly available on the web. That was part of it. But they also went further. They had internal data sets, synthetic data that they made specifically for teaching the model certain things. And they had these instruction tuning data sets where humans had actually annotated and corrected the model's output. And they even used some specialized data from vendors.
So it's like they were super careful about the quality of the ingredients, so to speak.
Absolutely. They did a lot of data optimization, which is so important. I mean, the internet's full of junk, right? So they actually boosted the amount of educational content because that's often really high quality. And they used machine learning filters to automatically weed out the low quality stuff.
Makes sense. You don't want the model learning bad habits from bad data.
Right. And they also deduplicated everything. So the model wasn't just memorizing the same things over and over. They used heuristic filters to make sure everything was safe and high quality. It's really like a chef carefully choosing the best ingredients for a complex dish.
Okay, so we got this massive data set. Now, what about the architecture, the model itself, how they design it?
They made some interesting choices, like, for example, their transformer block, which is like the fundamental building block of the model. They used a parallel transformer block, which is kind of like adding more lanes to a highway so you can process things faster, which obviously improves throughput.
So they're already thinking about efficiency.
Yeah, and they also removed these things called bias terms, similar to what Google did with their PaLM model. It might seem small, but it actually helps with stability, especially when you're training these huge models.
So it's like making sure the foundation is extra strong.
Exactly. And another thing they did was share the input and output embeddings. Command A has a massive vocabulary, so this really saves on memory usage without affecting performance. They actually did a lot of testing to make sure this didn't hurt how well the model understood and generated language.
Okay, so efficiency and stability seem to be big themes here.
Yeah.
What about the actual pre-training process, like the steps they took?
So their pre-training involved a lot of optimization, especially with these things called hyperparameters, which are basically settings for how the model learns. Now, instead of trying to find the perfect settings on their massive model, which would be super expensive, they do it on smaller versions first. They use these techniques called AMP and transfer, which let them apply what they learn from those smaller models to the bigger ones without losing much performance.
Smart. So kind of like practicing on a smaller scale before going big.
Yeah, exactly. It's much more cost effective.
Now, all this training requires crazy computing power, right? How they handle that with their NVIDIA H100 GPUs?
Okay, here's where it gets really interesting from a technical standpoint. They used JAX, which is this powerful tool for numerical computation, and they used JAX's GSPMD to do all sorts of cool stuff with sharding. Sharding is basically splitting up the work across multiple GPUs so you can train faster. It's like dividing a huge cooking task among many chefs.
So they're coordinating all these GPUs to work together efficiently.
Right. They used a few different strategies. There's data parallel, DP, where you have copies of the model working on different parts of the data. Then there's fully sharded data parallel, FSDP, where you split up not just the data, but also the model's internal state, which helps save memory.
Makes sense. Divide and conquer.
Yeah. And then there's sequence parallel, SP. Since these language models often work with really long sequences of text, SP splits those sequences across multiple GPUs. They also did some really clever stuff to minimize the time spent communicating between GPUs, like overlapping calculations in the feed-forward network with the communication needed for the attention mechanism.
Wow, it's like a carefully choreographed dance to make sure everything flows smoothly.
It really is. And then there's tensor parallel, TP, which is all about dividing up the model's weight matrices that sits knowledge across multiple GPUs, a bit like how it's done in a system called Megatron. This is especially useful for fast decoding and when you're using smaller batches of data.
So they had this whole toolbox of techniques. How'd they decide which ones to use?
They used different combinations depending on what they were doing. For the main pre-training, where they needed maximum speed, they combined DP, FSDP, and SP to reduce communication overhead. They even optimized the code to overlap weight transfer with calculations.
So squeezing every bit of performance out of the hardware?
Exactly. And they also took advantage of NVIDIA's Hopper architecture. These Hopper GPUs have FP8 tensor cores, which are specialized units for faster calculations using lower precision numbers. It's a trade-off. You get more speed, but you have to be careful about stability.
So it's like finding the sweet spot between speed and accuracy.
Right. They actually kept the model's main weights and the optimizer states in a higher precision format, FT32, and only converted to the lower precision formats, BF16 or FP8, right before doing the computations. They were very meticulous about it, even starting the training in BF16 before switching to FP8.
Okay, so we've covered the pre-training in detail. Now the paper talks about this decentralized post-training approach. What's that all about?
All right, this is where it gets really interesting. Instead of the usual way of fine-tuning a single model step by step on different datasets, they took this decentralized approach. They switched between fine-tuning a central model and training specialized expert models. Then they merged these expert models back into the central one.
So it's like having different teams specialize in different areas and then combining their knowledge.
Exactly. It gives them more control over how the model performs in different areas.
So what were the steps in this post-training process?
Okay, so first, they trained this instruct model using supervised learning. This basically taught the model the basics of understanding and following instructions. Then they trained 6 SFT expert models in parallel. Each expert focused on a different set of skills, like one for coding, one for multilingual tasks, and so on.
So each expert is becoming really good at its own thing.
Yeah, and then comes the cool part. They created the SFT soup model by merging these 6 experts. It's like combining the best qualities of each expert into one model.
That's where the soup analogy comes in.
Exactly. Then the soup model went through more training, this time using reinforcement learning, which resulted in the RL soup model. This step refined the model's behavior and made sure it produced the right kind of output. And finally, they had the final command A model. This involved a polishing phase where they focused on improving the writing quality and making the output more human-like.
So a multi-stage process, each stage building on the previous one.
Right. And they used some sophisticated reinforcement learning methods along the way. For preference training, where the model learns to choose better responses, they experimented with SLIC, DPO, IPO, and their own method called SRPO, self-improving robust preference optimization. For optimizing the reward signal, which guides the reinforcement learning, they used CoPG, contrastive policy gradient, in both offline and online settings.
Okay, so lots of technical jargon. What's so special about SRPO?
So SRPO is really interesting because it aims for self-improvement. The model tries to learn how to improve its own generations based on a preference model, but without making drastic changes to its behavior. It's also more robust to variations in the data, and it can even iteratively refine its output during generation, which is pretty unique.
So it's like the model is constantly trying to get better, even as it's generating text.
Exactly. And CoPG is interesting because it can be used in both offline and online settings, and it has some strong theoretical guarantees, meaning we can be more confident that it will learn effectively.
Okay, so they're using these advanced techniques to fine-tune and align the model. Now let's talk about what Command A can actually do, starting with instruction following, which seems like a fundamental skill.
Absolutely. Instruction following is all about understanding and executing commands given in natural language. For Command A, they focused on this through both supervised fine-tuning and offline preference tuning.
And how do they get the data to train it for this?
They had a really thorough process. Mostly, they automatically generated prompts and had humans annotate the model's responses, providing ratings and even rewrites. They created lots of different prompts covering various topics, especially those relevant to business, and they included multi-turn conversations to make it more challenging. They distinguished between data for supervised training, where they used those human rewrites, and data for preference tuning, where they compared differently rated completions.
So high-quality human-vetted data was key.
Right, and they also used this cool technique called iterative reward-based sample refinement. They used their own internal reward models, trained on the latest versions of Command A, to score both human-written and model-generated completions. This helped them pick the highest quality examples for training, even while the model was still under development. It's like a continuous feedback loop, improving the training data as the model improves.
Very clever. So the model is helping to train itself in a way. What about the different preference tuning methods they tried?
They experimented with slice, IPO, DPO, and their own SRPO for instruction following, and they found that SRPO worked best overall, so they chose a model trained with SRPO as their final instruct model.
Right, so instruction following is the foundation. But these days, LLMs are doing more than just following instructions. The paper mentions retrieval augmented generation, tool use, and agents. Why are these important?
These are the capabilities that turn LLMs from just chatbots into powerful tools that can actually interact with the real world. Tool use, which means being able to use external programs or APIs, analyze results, and make decisions based on them, is essential for both RAG and for automating complex workflows. RAG allows the model to access and use information from outside sources, which makes its answers more accurate and relevant. And agentic frameworks let the model chain together multiple actions, potentially using multiple tools to achieve more complex goals.
So it's about taking action, not just generating text.
Exactly. That's what businesses need.
How did they train Command A for these more complex agent-like behaviors?
They had a specific data format for tool use training. It included the user's request, the available tools, the model's reasoning about which tools to use, the actual tool calls and their outputs, and the model's final answer, often with citations. They had internal experts create this data in a style called React, which focuses on reasoning and acting. They also created synthetic training data, using other LLMs as judges to check the quality.
Sounds like they put a lot of effort into making the training data as realistic as possible. What about multilingual capabilities? That's a big deal for any enterprise-focused model.
Absolutely. They focused on 23 languages, which cover a large portion of the global population. They wanted to make sure Command A could handle the demands of global business.
So it's not just a model for English speakers.
Right. They trained it on a wide range of multilingual tasks, including translation, safety, reasoning, controllability, RA, and even agentic capabilities across languages. They collected data through human annotation, using existing multilingual datasets, and machine translation.
So they didn't just translate English data.
Nope, they had specific processes for multilingual data collection and annotation. They had separate processes for regionally relevant data and complex multilingual tasks. For the complex tasks, they used a mix of LLM-generated responses with human post-editing and manually annotated human data. They even built a custom platform for all this.
Impressive. And how did they ensure the quality of the multilingual data?
They used a multilingual best event approach. They had different expert models generate multiple responses, use their internal reward models to score them, and then selected the best ones for training. This often resulted in responses that were as good as or even better than human-written examples.
So using the models themselves to generate high-quality data, what about code capabilities?
Code was another big focus. They focused on 8 major programming languages and 5 dialects of SQL, aiming to be good at generating, translating, and optimizing code. They used a combination of annotation and synthetic generation for their data, and they enriched it with all sorts of contextual information: execution feedback, explanations, paraphrases, error messages, database information, and unit tests.
So they were really thinking about the context in which code is written and used.
Exactly. They prioritized code that had actually been executed successfully in a safe sandbox environment. They even enriched the pre-training data by automatically adding print statements and synthetic inputs to code snippets and appending the output. This added a lot of valuable data.
Smart. What about the reinforcement learning stage for code?
They jointly optimized for code correctness using unit test results as rewards, and for code style and formatting using preference data. They also used AI to generate examples for things like explanations and formatting, guided by reward models and human feedback. And finally, they did a second round of supervised learning using only the highest quality code data from their best experts, which really boosted their performance.
So a very thorough approach to code training. What about reasoning capabilities like logic and problem solving?
For reasoning, they focused on using synthetic data that had been carefully filtered to make sure the solutions were correct. For preference tuning, they used both human-rated comparisons and fully synthetic data sets with correct and incorrect solutions. They found that getting the correctness of the solution right was super important for reasoning, more so than in other areas.
It makes sense. You don't want the model learning to prefer bad reasoning.
Exactly. And they found that merging reasoning-focused models with general instruction-following models first was a good strategy before merging them with other experts.
Interesting. What about long context handling?
For long contexts, they created synthetic training data by taking long chunks of text and using an earlier version of their model, Command R plus refresh, to generate question-answer pairs based on those texts. Then they used their reward model to select the best pairs and combine them with the original texts for training.
So bootstrapping from an earlier model to create training data for longer contexts. Now let's talk about safety. How did they approach that?
Safety was a huge priority for them. They did extensive filtering during the pre-training data preparation to remove harmful and low-quality content, including sexually explicit material. Then, during post-training, they used both direct training data and preference data that was labeled by internal and external safety experts. They even used AI personas and rephrased harmful prompts to make the safety training more robust.
Sounds like they were thinking about a lot of different ways that safety could be compromised.
Yeah. They also recognized the need to balance safety with helpfulness, so they split their safety data sets into ones focused on increasing safety and others focused on ensuring helpfulness. They found that a method called IPO worked best for this type of training. And they said the polishing stage had a big positive impact on safety as well.
So, a layered approach to safety, from data filtering to specialized training. Now let's get into one of the most interesting parts of the paper. Model merging. What exactly is that?
Model merging is all about combining the learned parameters, the knowledge of multiple AI models into a single model. They used a mathematical function to combine these sets of parameters.
Why merge models instead of just training one giant one?
Merging has some key advantages. It's faster than running multiple models separately, uses less memory, and in the case of Command A, it allowed them to combine expert models that were really good at specific tasks into one model that could hopefully do it all. It's like creating a super expert by combining the knowledge of many specialists.
So the soup analogy applies here too.
Yeah, it's like blending together different expertise. They mainly use expert merging, but they also mentioned other types of merging. Merging snapshots of the same model during training to smooth out learning, merging models trained with different random seeds to reduce the impact of randomness, and interpolation merging to restore certain capabilities.
But expert merging was the star of the show for Command A. What were the benefits they found?
Expert merging was crucial for their strategy of developing different capabilities in parallel. It allowed different teams to focus on their own specializations and then combine their work. It also let them optimize the training process separately for each capability, since things like coding and safety might need different amounts and types of data. And it made it easier to evaluate the model on a huge number of metrics, which helped them design the final model.
So it's like a more agile and flexible way to develop these large models.
Exactly. What kind of merging function did they use?
They mostly used linear merging, which is basically taking a weighted average of the parameters from different experts.
Right.
They manually experimented with different weights to see what worked best. They did try more complex methods, but they didn't see enough benefit to justify the added complexity.
They also highlighted the importance of consistency over optimality. What did that mean?
They found that starting all their experts from the same base model that was good at general instruction following was really important. This helped ensure that all the experts could handle special instructions and didn't lose performance on tasks like processing long texts. They even used a leave one out technique to check if any expert was hurting overall performance. Their key takeaway was that making sure the experts were compatible was more important than just squeezing the best performance out of each one in isolation.
It's like making sure the team members can work well together.
Exactly. And they mentioned that merging is cheap, evaluation is expensive. Why is that important?
It's a practical consideration. While merging itself is computationally cheap, evaluating the merged model across tons of different tasks and metrics is very time-consuming and resource-intensive. So a lot of their effort went into designing the training process for each expert to make them more compatible for merging, rather than just focusing on the merging algorithm itself.
So planning and evaluation are just as important as the merging technique itself. Now, after all this merging, they have a polishing phase. What's that for?
Polishing is all about fine-tuning the final model to align it with human preferences in terms of writing style and addressing any issues introduced during merging. It's about making the model not just capable, but also pleasant to interact with.
What are the steps involved in polishing?
They do more supervised learning on their best data, using their reward model to select the best generations. They do more offline preference tuning. And finally, they use online RLHF with their CoPG method, where they generate 2 responses for each prompt. They also use some regularization techniques to keep the model stable. They found that alternating between offline and online preference learning was very effective.
So there's a final layer of refinement to smooth out any rough edges. Now, for the big question, how well did Command A actually perform?
They did a ton of evaluation covering a wide range of benchmarks. On general academic benchmarks, it performed very well, often beating models of similar size and even competing with much larger ones.
Impressive. What about the agent-like capabilities?
It got great results on tool use benchmarks, showing it can handle complex tasks that involve interacting with external systems.
And multilingual performance.
It excelled in multilingual tasks, including translation and various other benchmarks, confirming its ability to handle multiple languages effectively.
Code generation and understanding.
It showed strong performance in Python and other languages across various code benchmarks, and it got even better when used as a code agent with tool use.
Reasoning and problem solving.
It achieved competitive performance on reasoning tasks, demonstrating its ability to handle logic and complex problems.
Safety and robustness.
It performed well in various safety evaluations, showing robustness to things like demographic changes in prompts.
Real-world enterprise use cases.
It achieved high success rates on their internal enterprise benchmarks, confirming its readiness for real-world business applications.
Long context handling.
It showed good capabilities in handling long sequences of text, which is crucial for many tasks.
And what about the merging process itself? Did it work well?
Their analysis showed that merging was effective at preserving the performance of the individual experts, with only a small average drop in performance across different tests. RAG and general performance were especially well preserved. They also found that merging worked well even at large scale, and that a bit of post-merge fine-tuning helped.
In the final polishing step.
Polishing led to significant improvements, especially in aligning the model with human preferences. People who evaluated the model preferred it over other advanced models, particularly for its adherence to formatting and style requests.
So it sounds like Command A is a big step forward for enterprise-ready LLMs.
Absolutely. It achieves top-tier performance across a wide range of tasks while also being efficient.
What were the key innovations that made this possible?
Their careful data choices and architecture during pre-training, their innovative decentralized approach to post-training with expert merging, and their effective techniques for self-refinement and polishing.
For our listeners who want to learn more, where should they go?
The full Command A research paper is definitely worth a read. It has all the details about their methods, experiments, and results.
So as a final thought, with the arrival of powerful and efficient enterprise-ready LLMs like Command A, what new possibilities might this open up for AI applications in business and research? That's something to ponder. Thanks for joining us for this deep dive.